In this video, I'm going to go through AQA AS-level Chemistry, the second half of paper 1. This is the 2017 paper. I did the first half of this paper in an earlier video, so starting off with question 8 here. So it's paper 1 AS Chemistry 2017. Right, when acidified solution of sodium nitrite is added to aqueous potassium iodide, iodine and nitrogen monoxide are formed. Give the oxidation state of nitrogen in the following species. So we're going to use this. Sum of the oxidation numbers is equal to the charge on the species. Right, so let's do the nitrite ion first. The charge on the species is going to be -1. Nitrogen we don't know, so call that N. Oxygen has always got an oxidation number of -2, so there's 2, so that's -4 for the oxygens. So nitrogen is equal to, take that to, is equal to 1. Sorry, -1 there. So it's going to be equal to +4 -1 is equal to +3. And then with the nitrogen oxide, so the charge on the species is 0. So N -2, so nitrogen is equal to +2 in that one. Write a half equation for the conversion of nitrite into NO. Right, let's do that. So we're going to have NO2 minus going to NO. Balance for the oxygens with water, so we need to put a water on the right hand side. Now balance the hydrogens with protons, so we need 2 protons on the left hand side. Now balance for charge, we've got 0 charge on the right hand side, and we've got +1 the moment on the left, so we need to put a negative electron in there to balance it out, plus E minus. And then you can check with the oxidation numbers because look, it's gone down from +3 to +2, so it's a reduction by 1 electron's worth, and that's what we've got there. We've got gaining 1 electron, so that looks right. A half equation for the conversion of iodide into I2, so that's a bit easier. So we're going to have I minus goes to I2. Well, we need to balance for the element, so we need a 2 there. No oxygens or hydrogens to worry about, so just the charges. We've got 2 minus on the left and 0 on the right, so we need to put add 2 electrons to the right hand side of the equation, 2E minus. Right, write an overall ionic equation for the reaction of NO2 in acidic solution with I minus. So we've got to combine these two half equations here. Now the top one is only 1 electron, so we've got to multiply that by 2, so we've got the same number of electrons on both sides. So we are going to get 2 nitrite ions, 2 protons, sorry, 4 protons it's going to be, double it. And then we've got 2 I minus is going to go to 2NO plus 2H2O and I2. So that's our balanced equation. State the role of the nitrite in the reaction with, right, so the nitrite, that gets, we've established that that gets reduced. So that means this is behaving, it gets reduced itself, so it's an oxidizing agent. It takes electrons off other things, gets reduced itself, oxidizes the other thing. Right, in aqueous solution, nitrite ions react with acidified chlorate 5 ions according to this equation. Right, so we've got to calculate in grams per decimeter cubed the concentration of the sodium nitrite in the sample. Okay, so what have we got here? They give us the volume and the concentration of potassium chlorate. So we can work out the moles of potassium chlorate. So let's do that. Moles of the chlorate ion. 1 mole, obviously, K, 1 mole of potassium chlorate contains 1 mole of chlorate ions. So that's concentration times volume. That is equal to right. Let's do that. 0.02 concentration multiplied by 27.4 here over 1,000 because it's got to be in dm cubed. That gives us 5.48 times 10 to the minus 4 moles of chlorate. So how many moles of nitrate is that? Nitrite, sorry. So 2 moles of chlorate react with 5 moles of nitrite. So therefore, right, the moles of nitrite are going to be 5.48 times 10 to the minus 4. That's the moles of chlorate multiplied by 5 over 2. Okay, and that gives us 1.37 times 10 to the minus 3 moles of nitrite. Right, let's work out the concentration of the nitrite then. So this was in 25 centimeters cubed. So conc of the nitrite, which is equal to the concentration of sodium nitrite, yeah, it's 1 mole, okay, is equal to moles over vol, 1.37 times 10 to the minus 3 divided by 25 over 1,000. That gives us 0.0548 moles per decimeter cubed. Right, but we need the concentration in grams per decimeter cubed, not in moles per decimeter cubed. Well, we've got, how many moles have we got in 1 dm cubed, right? So in 1 mole in 1 dm cubed, we have 0.0548 moles of sodium nitrite. So we need to work out what is the mass of that in grams. So mass is equal to moles times mR. Well, the moles we've got is 0.0548, and the mR of this stuff is going to be 23 plus 14 plus 2 times 16, which is equal to 69. Okay, so that's times 69. So that gives us an answer of 3.78 grams, and that is in 1 dm cubed. So that's the concentration of the sodium nitrite in moles, in grams per decimeter cubed. Okay, so we're onto our multiple choice section now, which is the correct crystal structure for the substance named. Right, iodine's giant, sorry, diamond is giant covalent, so that's definitely wrong. Sodium chloride is ionic, so that's definitely wrong. Graphite's not a metal, there's got to be that one. Iodine is simple molecular, I2 molecules held together by van der Waals forces. The best technique to remove silver chloride, which forms when aqueous solutions of sulfur nitrate and calcium chloride react. Well, you remember there you get a precipitate of AgCl solid. So separating the solid from the solution, the best thing is to filter C. Which statement about astatine is correct? If you look, astatine is the element below iodine in group 7. So it's going to be, it's not very common because it's radioactive, it's very rare. But what can we say? Right, what happens to the electronegativity as you go down the group? The E negativity decreases. So that's going to be wrong. It's going to be less electronegative than bromine. Right. It's not going to be a better oxidizing agent, because what is the best oxidizing agent is that, right, imagine all these. It's the element that wants electrons the most. Who wants electrons the most is fluorine. Yeah, that is a very powerful oxidizing agent. It's got very strong tendency to take electrons and form fluoride ions. So astatine is going to be, they get worse as you go down the group. As they get bigger, it's harder for them to pull in electrons because their nucleus is shielded more. So that's wrong. It will have a greater boiling point because the van der Waals forces are going to get bigger as you go down the group. That's true. And a first ionization energy in bromine. No, that's wrong as well. The first ionization energy of any group in the periodic table decreases as you go down the group. Every single group 0, group 1, whatever, because you're getting more shielding and the nucleus is further away from the outer shell. So C is the answer there. Which statement about time of flight mass spectrometry is correct? The current in the detector is proportional to the ion abundance. That is true. Let's check the other ones. Sample particles gain electrons to form positive ions. Well, they don't. They lose electrons. Particles, for anything to fall, you gain an electron, you're going to become negative. So that's definitely wrong. Particles are detected in order of the kinetic energies. No, because they all have the same kinetic energy. And they've got different speeds because they've got different masses. The ions are accelerated not by a magnetic field, by an electrical field. So that's wrong. Okay. Chlorine exists as two isotopes in the ratio 3:1. Which statement about peaks in the mass spectrum of chlorine is correct? Well, I'm going to spend a little bit longer than you probably would spend on this in an exam, but let's say you've got a chlorine molecule. Let's say you've got Cl2. Right, so we're going to say the first chlorine is, so this is 35. It could be 35 Cl or it could be 37 Cl. And then we're going to have the second chlorine. Well, it could be 35 Cl or it could be 37 Cl. And then for the second one, it could be 35 Cl or it could be 37 Cl. You probably remember doing these diagrams, GCSE maths, probability. Right, so what's the probability of the first one being 35? Well, it's 3:1, so it's 3/4 is the probability of that. Whereas this one, the probability of being 37 is only 1/4. Let's do the second one. The chance of the second one being in a molecule being 35 is also 3/4, and that one's going to be 1/4, and this one's going to be 3/4 and 1/4. Now, what's the probability of having two 35s as you do that? Well, it's 3/4 times 3/4. That is going to be 9/16 is the probability of that one. This one is going to be 3/4 times 1/4, so 35 and a 37. That's going to be 1 times, that's 3/16 for that. This one is going to be 1/4 times 3/4, that's 3/16. This one is going to be 1/4 times 1/4, that's going to be 1/16. Right, what would be the mass of this one? Well, 2 35s, it's going to be 70. The mass of this one is going to be a 35 and a 37, 72. That one's going to be 72. And this one's going to be 2 37s, 74. So you can see these two are combined. So the chances of getting that one is 6/16. This one is 9/16. And this is 1/16. So the ratio is going to be 9:6:1. That is the answer there. So again, you probably wouldn't spend that long in an exam doing it, but that's a fairly, that crops up quite a lot, that question. Okay. Right, number 14. Right. 4.85 sample of sodium anhydrous sodium sulfate, so that's going to be Na2SO4, is dissolved in water and the solution made up to 250. What's the concentration of the sodium sulfate? Well, the MR of that is going to be 23 times 2 plus 32.1 plus 4 times 16, which gives us, 1 minute, That gives us 142.1. Right, so how many moles of it we got? Moles of sodium sulfate is equal to mass over mR. That's 4.85 over 142.1, which gives us 0.0341 moles. Now the concentration is equal to moles over vol. Then moles is 0.0341, and the volume is 250 centimeters cubed. That's 0.25 dm cubed. And that gives us an answer of 0.137 moles per decimeter cubed. It's this one. Okay, which of these contains the greatest number of atoms? So what we're going to have to do here is work out the number of moles, okay? Now, I'm just going to do moles of I, not I2 here, okay? Moles of I is equal to mass over mR over the AR, really, because it's an atom. Well, that's 127 milligrams is 0.127 over 127. That is equal to 1 times 10 to the minus 3 for that. This one, phosphorus, so that's going to be, right, it's going to be mass over AR. We've got 1.54 times 10 to the minus 4 kilograms, which is multiplied by 1,000 to give us the grams. So that's 0.0154 grams. Divided by phosphorus is 31. So that gives us 4.96 times 10 to the minus 4. Okay, so the iodine's winning at the moment. 81 milligrams of carbon dioxide, well, that's going to be equal to 0.081 grams over the mR of carbon dioxide is 44. That is equal to 1.84 times 10 to the minus 3, no, molecules. We've got carbon dioxide, it's got 3 atoms per molecule, so times that by 3, that is going to give us 3.5 times 10 to the minus 3 atoms. So that's the highest so far. Let's do ammonia. 1.7 times 10 to the minus 4 kilograms. How many grams is that? That's 0.17 grams over the MR17. That gives us 0.01 moles. We're going to multiply that by 4 because it's NH3. So that's going to be equal to 0.04 moles of atoms. That's the most number of moles of atoms, so the answer is D. There's a lot of working out for your 1 mark there, really. Not very hard, but there's a lot of working out. Okay, this one about titration technique. Right, so you're going to get NaOH in a beaker, and you're going to pipette that out and put that into a conical flask, and then titrate that against ethanoic acid. Right. The concentration of the ethanoic acid calculated from the experiment result was found to be lower than the actual value. Okay, so right, what could explain this? If you rinse the pipette with distilled water before filling with NaOH, now if you did that, that means you are not going to get be less NaOH in there than there should be. So that means you're going to use less acid. So you're going to think the acid is more concentrated than it really is, not less. So it can't be that. Rinse the burette with distilled water before filling with ethanoic acid. Right. Now that would dilute the acid. So you need a greater volume of it. So you'd calculate that the concentration would be lower. So that's the correct one. Okay, let's just try, just check the other ones. Rinsing the walls of the conical flask with distilled water during titration, that won't affect the result at all. That's fine to do that because you're not changing the number of moles of NaOH in the conical flask. Rinse the beaker with distilled water before filling with NaOH. Well, that would dilute the NaOH, which would do the same thing as A, which we've already said is going to give us a higher value, not a lower value. So B is that one there. A lot of thinking in that one, in that question. Okay. 17. Right. 20 centimeters cubed of 0.4 of aqueous solution of metal bromide, okay, reacts with exactly this volume and this concentration of silver nitrate. Okay, so silver nitrate reacts, Ag plus reacts with 1 mole of bromide ions to form a precipitate of sodium bromide. Okay, now what we need to do is work out the number of moles of silver plus we've got there. So moles Ag, conc times volume. So that is going to be 0.1 times 160 centimeters cubed is 0.16 dm cubed. So that's 0.016 moles of silver. Now let's work out how many moles of MBr we've got. We've got concentration times volume. So we've got 0.4 multiplied by 20 over 1,000. That gives us 8 times 10 to the minus 3. Let's write it down as 0.008 moles of MBrX. Now look, we can see that these react in a 1 to 2 ratio. So that means that contains 2 moles of Br minus ions. So the formula is this one, MBr2. 18. Which species has one or more bond angle of 90 degrees? Well, methane is tetrahedral. They're all 109.5. That's wrong. This one is also tetrahedral. You've got 4 bonding pairs in NH4. Right, yeah, so that's 109.5 because you've got three normal bonds and 1 dated bond. Aluminium chloride, well, if you check the AlCl4 minus, sorry, well, aluminium is in group 3, forms a covalent chloride. That's AlCl3. AlCl4 is when you get a chloride ion, it comes in here and forms a dated bond. Okay, so that aluminium has got 4 bonding pairs and 4 lone pairs. Sorry, 4 bonding pairs and no lone pairs. It's tetrahedral, 109.5. So the answer has got to be C. And just to check that, I'll just that is actually what you've got there. If you draw the structure of that, again, I'm going to spend a bit longer than you would do in an exam, really, just to explain. You've got ClF, okay? So we've got chlorine, dot, 3 single bonds. The fluorines, of course, 9 electrons in the outer shell, so sorry, 7 electrons in the outer shell, so there's 3 lone pairs on each fluorine. I won't bother drawing on all of them. The chlorine, right, this is in group 7, and we've only drawn, I've drawn 3 dots there, 3 of the chlorine's electrons. So it's got 3 other ones, hasn't it? It's got 4 other ones because it's in group 7. It's got 2 lone pairs. So it has got 3 bond pairs and 2 lone pairs. And so the shape of that molecule is usually described as T-shape because if you remember, when you've essentially got five 5 pairs of electrons there, yeah? When you have 5 pairs of electrons, you remember the shape, such as PCl5 is a classic example. What you have is you have 3 electrons in a triangular planar thing there, like that, and you have one sticking up, one sticking down, so 3 bonds there. Right, so that's not phosphorus, it's chlorine, and it's bonded to 3 fluorine atoms. So you've got one there, and one there, and these two things are lone pairs. Right, so you can see that the bond angles there are going to be 90 degrees because that's sticking up into that flat plane. So this one is the answer there. It's usually described as a T-shaped molecule, that, and that comes up. They ask you for the shape of that. You look at a lot of AQA past papers, they get you to work out, things with, I don't know why, because they're very rare molecules, but on their papers all the time, things with 3 bond pairs and 2 lone pairs is quite common on past papers, and it's T-shaped, and you've got 90-degree bond angles about. Right, about equilibrium now. So we've got this equilibrium. Right, which statement is correct? Total pressure is increased, yeah? The proportion of that will go down. It won't, it will go up, because if we increase the pressure, that reaction is going to go backwards, because we've got 1 mole on the left and we've got 2 moles on the right. So increasing the pressure will give you more COCl2. So that is wrong. Using a catalyst will increase the proportion. Catalysts don't do anything to the positions of equilibrium, so that's wrong. Reducing the equilibrium concentration of CO will increase the value. No, the only thing that changes equilibrium constant is changing temperature. Changing pressure, changing concentrations does not change Kc, so that's definitely wrong. So this one must be right. Let's just check it. Raise the temperature will increase the value of the equilibrium constant. Right, that is right. Look, this reaction is endothermic. Okay, so Kc, right, is going to be concentration of CO, Cl2 over that. Right, so it's endothermic. So if we increase the temperature, it's going to make the reaction go forwards. So this is going to get bigger. That's bigger on the top. So that's going to make Kc bigger. So that is the answer. Right, which of these is not a redox reaction? So we've got to look for where we don't have any changes in oxidation numbers. Okay, right, you see here copper's +1, and here it's +2 and 0. Yeah, that's redox. Right, there's no change in oxidation number in B. Magnesium is always forms a 2+ ion, so it's 2+ throughout. Chlorine is 1 minus in both of those compounds. Oxygen is -2, hydrogen is +1. That's the answer. Let's just check these. So you can see tin here is going to have oxidation number of +2, but here it's been oxidized to +4. And you can see the mercury there is going to be -2. Here it's the element, so it's 0. Let's just check our manganese here. So that's going to be +4, but there it's only +2. And you can see that the chlorine there, look, that's -1, but here's an element, it's 0, so it's changed. So B is the right answer. Right. Which of these has the highest first ionization energy? Put the periodic table there. Right. So we're looking at sodium, aluminium, silicon, and chlorine. Well, you probably know as you go across the periods, the general trend is for an increase in ionization energy due to increasing nuclear charge. And so chlorine is probably the right answer. Let's just check that. There are a few little dips there. Do you remember as you go across? So it dips when you go from magnesium to aluminium. You get a little dip because aluminium's got a lower first ionization energy because it's coming from the 3p. Sulfur's got a slightly lower ionization energy than phosphorus because you're getting pair repulsion, but none of those things apply. Chlorine has got the highest one. Chlorine is the answer there. The empirical formula of an oxide of nitrogen that's 26% nitrogen. So let's say in 100 grams, we've got 26 grams of nitrogen, and that means we must have 74 grams of oxygen. So the moles, we're going to divide the mass by the MR. So that's going to be 26 over 14 for nitrogen and 74 over 16 for the oxygen. That gives us a 1.86 to 4.625 molar ratio. Divide by the smallest number, 1.86, gives us 1 to 2.5. So that's going to be N2O5, that one. Okay, which species is not produced by a redox reaction between solid sodium iodide and concentrated sulfuric acid? Right, now this is, and these all are, right? Now you can tell that these are redox reactions because sulfuric acid, H2SO4, the oxidation number of the sulfur is +6. Here it's -2, here it's 0, and here it's +4. So there's some redox going on there. The oxidation number has changed. But the oxidation number of sulfur and sodium sulfate is still +6, so there's no redox going there. Not saying you don't make any, but there's no redox. And that is the end of that paper.